Hi, welcome to Shuley Physics. This is review session 3 for the AP Physics Mechanics exam. Looking at work, power, and conservation of energy. All right, here we go. So work's change in kinetic energy, and it's also a force times a displacement. Now that is two vector being multiplied together, so it's a vector product. Excuse me, it's a scalar product. And the reason is, if we look at this diagram down here, if you take a crate or box or an object, something like that, and you push it along the floor with a force F, which way will it move? It'll move along the floor. It'll move and it'll be displaced in the direction of the floor. So the displacement is, in this scenario, to the right, and the force is being applied at an angle. Now, if you push straight down on the box, it will not be displaced, but if you push horizontally in the direction of the displacement, direction of the floor, it's going to be displaced. So you can do work if you push it horizontally along the floor. So it's the horizontal component of the force, or if you look at this angle reference for the theta right here, it's the adjacent component to the angle. So that aligns nicely with using the scalar product. In addition, work has no direction. It is a scalar, not a vector. So everything agrees there. If you take F times the cosine of theta, that is the horizontal component of the pushing force, and delta X is the displacement. So just the scalar product, A dot B equals AB cosine theta, agrees perfectly with work here. So I'm going to do all that ugliness. I'm going to be using that as we continue here. So there's the A dot B equals AB cosine theta, the definition of a scalar product, and it fits perfectly with work. Okay, so what does it mean? What's it do? Well, I'm going to scroll down here for a moment. Actually, no, I like this. We'll go ahead with the graph. If you also look at the graph of work, if there's a 20 Newton force that's applied constantly over 10 meters, then the work done is going to be 200 joules of work, 20 times 10. So what is that? That is, if you look at that on this graph, that is taking the side of this rectangle being 10 meters long, and the other side of the rectangle being 20 newtons high, and multiplying them together. You're finding the area. Okay, so how would you look at this from a kind of a calculus perspective? We just found the integral of that y equals 20 function that's applied over 10 meters, from 0 to 10 meters. So what if this force is changing? What if it's not a constant 20 Newton force? Then the area wouldn't be as big, because we'd have sort of a triangular shaped area. So would there be as much work done? If the force being applied to the box was a constant 20 newtons, we do a lot more work than if the force was increasing from 0 to 20 over that 10 meter distance. So we would get the area of this triangle is, think of like a triangle 1/2 base times height. So that's the little formula here. 1/2 base times height is 100 joules of work. And that's exactly half. It's this rectangle cut in half, or the work that's cut in half. So again, what you can think about when you're looking at a graph, if this isn't coming naturally to you, if you see a problem like this on the AP test, it's a graph. So you think to yourself, what does the data reveal? Well, the data reveals how the force is being applied over a displacement, over a distance. You think about the slope, is F divided by X? Is force divided by X anything meaningful? Not really. Then what about the area? What about the area? Area would be F times X, force times displacement. Look that up on your equation sheet, and you'll find that under work. So the work is the area in this, under this plot, under this graph. So what if the mass is given? That's an interesting question. Can we figure out anything if we know the work done and the mass, or the force and the mass? Well, you could if you divide all these force values by the mass, this could be an acceleration versus displacement graph, how acceleration changes. If force is constant, then acceleration would be constant. But what about down here? If force is increasing, then acceleration is increasing. Now, usually you don't have any good quantities to compare acceleration to displacement with. So moving on a little bit, there is a little bit more we could determine. It's actually rather easy to figure out the final velocity if you know the starting velocity given something like this, the work done in this triangular area here. And that brings us to the Work-Kinetic Energy Theorem. We're going to come back to that graph in a moment. You see, work isn't just this thing we in physics we just say, oh, here's the work equals force times displacement equation. Okay, it comes from somewhere. Work and energy is just a tool. It's a mathematical tool. It's a way of thinking to conceptualize what's happening. There's not like a blue bar of energy that is going into this box as we push it, as you might see in video games. It's actually just coming from Newton's second law of motion. And if you take a acceleration, a constant acceleration, and recall that Vf squared equals V0 squared plus 2ax, you reformat that algebraically, a equals Vf squared minus Vo squared divided by 2 delta x. If you plug that in for a up here in Newton's second law, you get m times all that, m times Vf squared minus V0 squared. And what I've done here is I've brought this delta x up to the f. So we get a f times delta x equals this change in velocity squared times mass over 2. And just reorder that, and you get what's called the Work-Kinetic Energy Theorem right in there. Interesting thing. And this is where work and kinetic energy, change in kinetic energy, come out. So if you do know the work done, coming back to the graph, if you do know the work done by a force, even a changing force, here's a 100 joules, then that's also the difference in the kinetic energy. So you see, if you do know the mass of the object, you could also figure out the change in velocity. If the initial velocity of the object is 0, you could easily calculate the final velocity. So always keep that in mind, that Work-Kinetic Energy Theorem, it's coming from Newton's second law and an application of one of our equations of straight line motion. Now what if we do have a function that's a little bit more difficult to calculate an area for? Here we just took an area of a triangle. So what if a function is something like 1/2 x squared plus 1? So work then becomes, in a more calculus kind of a form, rather than looking at the area under the curve graphically, we can use the integral. So we can integrate work equals the integral of the force function dx. So if we go from 0 to 10 meters and we plug in that function, we can come up with a value and value for that work done. So because this is an exponential function, it's just sketched out here. We are getting a different amount of work out of that. Okay. So moving on, where does potential energy come in? Well, if I lift an object up, I got to do work to it. Okay. So potential energy is found when there are conservative forces involved. Conservative forces are gravity or the spring force. Forces where if you put energy in, it's not lost. So if I scoot an object across the table and let go of it, it'll continue sliding and eventually come to a rest. So the kinetic energy I put into that box or that object is going to be released or transferred to the environment around it in form of heat or thermal energy. The friction between that object and the floor is going to rattle the molecules and the atoms between the box and the floor, so that motion is going to transfer into the motion of molecules or vibrational molecules in the environment around it. So that's a non-conservative force. Friction is a non-conservative force. But if I lift an object up, it also stops. But it doesn't just stop and stay there. It would fall down if I let go of it. Toss an object up, it comes back down. push an object forward across a table, it just stops. So there's two different things that happen there. If I lift an object up, gravity also slows the object down and stops it. So there's a change in kinetic energy. However, that gravity will put that energy back in. It'll increase the energy, the kinetic energy again. But it'll be the not my lifting force that's increasing the kinetic energy. It'll be the gravitational force pulling it back down. So as I lift an object up, the work done is the weight times the height. That's the force times displacement. And cosine 180, yeah, so my displacement is upwards right here, but gravitational force acts down. So the angle between the force and the displacement is 180 degrees. So if you think about that, this cosine of 180 gives us a negative out front of the mgh. So the work done is a negative change of potential. The initial height is 0, the final height is whatever it is above the ground. So that's kind of a positive change. However, we get a negative work done. So the work translates into a negative change in potential energy. So if we apply that to a couple of different forces, conservative forces, let's look at gravity from a universal perspective. We have two masses that are a set distance r apart, and we move them away or move them closer. If there's a starting r and a final r distance, notice there is a negative in here also because it's a conservative force. That's where the cosine 180 comes in. This is a f of x times dr, where f is a vector and r is also a vector. So what we don't really see here is a little dot product. So that's why I'm including the cosine 180 there. So we get the negative sign involved in this expression. It's also showing it's a conservative or attractive force. Okay, so if we plug in the universal law of gravitation, right there, gm1 m2 over r squared. G is a constant, you might recall, but we take the integral of this. Our negative is still out here, but the integral of 1 over r squared is negative 1 over r. So there's our negative coming in here. And we get a gm1 m2 over r. And now we're going to apply our bounds r1 and r2 to get gm1 m2 over r2 minus gm1 m2 over r1. Now since that's the work done in lifting up, what are we doing? We might be launching off from the surface of the Earth, from let's say the radius of the Earth to 2 times the radius of the Earth. So from a smaller number to a greater number. I'm going to come back to this in a second. But that rocket is going to be doing work to lift that rocket off. It's going to change its kinetic energy and make it go faster. But as it increases, as it goes higher, it's going to give a negative change to the potential. So work equals a negative change of potential. So if we just think about that, what is an equation for potential energy of an object like a rocket launching off the surface? Well, this is the second potential energy state here, right? If we put in terms of U2, and this is the first potential energy state, U1. And if we look at it in terms of a negative U2 minus U1, all right, and we apply that negative, we get a negative U2 plus a U1. So to go from this form to this form, you'll notice that this gm1 m2 over r squared has to be a negative value, negative gm1 m2 over r2. I said r squared, I didn't mean r squared. And this value over here, if we apply this out here, we're adding u1. Well, that means u1 has to also be a negative for this expression to remain the same. In other words, if we plug in our potential at u2 being a negative value, negative gm1 m2 over r2 at that point, and we plug in that same expression over here, we're going to get positive gm1 m2 over r2 minus gm1 m2 over r1. Okay, so the negative applied in here, negative times a negative is a positive. You see that? This negative expression times this negative gives us the positive. And also the negative potential energy times a positive will give us that negative. So just to show you, the actual potential energies at these points is a negative function, negative inverse function. And that's where we're getting this curve. This is a negative 1 over x function. So what is that? I mean, how's that work? I mean, these are negative energies. So let's just say this value at radius of the Earth, let's just say it's negative 4. And what about the potential energy here? Let's just say it's negative 2. It's higher. Okay. Now, on a vector scale, you might be thinking, well, negative 4 is greater than negative 2 because the magnitude 4 is greater than the magnitude 2. But is energy a vector? No, it's a scalar. So what is higher on a scalar scale? Negative 2 or negative 4? Negative 2 is more positive than negative 4. Negative 2 is higher or greater on a number scale than negative 4. You see that? These are just numbers. So if you go from negative 4 to negative 2, you've increased the potential energy, right? And is that what's happening here? Let me get rid of all my scratches here. We're going from this starting potential to this final potential. Now the final has a greater R value than the initial. We're at twice the radius of the Earth here than we are over here. So if we divide by a bigger number, we end up with a lesser value on the left and a greater value on the right. That means this number over here is a bigger value than this number, and our total change is going to be a negative change. You see, work is a negative change in potential. So what will that look like in conservation of energy? Well, in a moment, we're going to revisit conservation of energy, but if you think about a planet moving in its orbit, or this could be this planet X here, let's say it's a highly elliptical orbit. Okay, it's not exactly circular here. What will its potential energy be at a certain point versus its kinetic energy? Well, if we look at the total energy value, it will be moving with a velocity v, and remember v is a vector, so but the v dot v times v squared here, will cause this kinetic energy to be a scalar value. You can also see that energy is scalar because it's a v dot v. It can't cross it with itself. So this is a positive value here. This is a positive kinetic energy. And we're going to add a negative, there's that negative again, that negative potential energy, g, mass of planet times mass of the sun, divided by r. And this is how you would include it in a conservation of energy equation. Now moving on, we get to a spring. So what about potential energy of a spring? If we take Hooke's law, spring force equals negative kx. There's that negative again. It's a conservative force. If we pull the spring outward, the restoring force is back inward. If we squish the spring inward, the restoring force is back outward. So the force is in the negative direction, the opposite direction of the displacement. Well, we plug that force in, negative kx dx, and we're going to do work on it from its rest position 0 to some position x. Later on, you can do x final there if you want to. Now the spring has a spring constant k, and we're going to displace that spring a delta x. So remember, there is no energy, no potential energy in a spring if it is not stretched out from its rest position. So all these displacements are measured from the rest position of the spring without any forces being applied to it. So we take that integral and we get a negative kx squared over 2. And here again, we're showing that the work done is if it's a negative change of potential, then that negative drops out, and we see that the potential energy of a spring is 1/2 kx final squared minus 1/2 kx initial squared. That would be the change of potential. So therefore, the potential energy of a spring at any displacement is just 1/2 kx squared right up there. Okay, so we use that oftentimes in physics as well. Okay. One little note, a little jump ahead to rotational motion. Keep in mind there's two kinds of kinetic energy we'll be looking into. Of course, there's the translational kinetic energy, 1/2 mv squared, and there's also the rotational form. When we look at the rotational analog of mass is rotational inertia or moment of inertia, and the rotational analog of velocity is angular velocity. So 1/2 I omega squared. So do keep in mind that total kinetic energy is the sum of the translational and the rotational kinetic energies. All right, moving along to a power. Power is a kind of candy of sorts. It's usually like a bonus FRQ question relating to power or the dissipation of energy over a certain time. So keep in mind that power has a few different forms. Power is rate of work done, work over time. So how quickly do I do the work? Since work is a displacement times a force, you could also think of it as force times displacement over time. You could also think of it as work is also a change in kinetic energy. So if you've got a change in velocity and a mass and a time, then you could also figure out power that way. So keep in mind all these different forms of work. And finally, if we look in here a little bit, you see this delta x over delta t. You might recognize that as an average velocity. So if there's a force being applied and let's say a constant velocity, good example is an elevator. A constant force is applied to an elevator, but it doesn't accelerate because that gravity is taking away the kinetic energy as it rises up. Then if you've got a constant velocity and a constant force, then the power output is Fv for that, F times average velocity for that elevator. Okay. Let's see, for a car, what's the power output? The car speeds up from 20 meters per second to 40 meters per second. It's got a mass of 1,000 kilograms, and it does that job in 10 seconds. What's the power output of that car? So that's another scenario there you could look at. What about pushing on a block where there's friction involved? Okay, so let's do a little bit of a power work here also. The power for the push, how powerful is the push? That would be the force times the displacement times the angle. So Fx cosine 30 divided by 20 seconds. That gives us 217 watts of power. What's the unit for power? Exactly. Watts is the unit for power. All right, then we have a negative force done by friction. So I'm going to substitute mu times normal force in for friction. And it's a negative force applied again over 50 meters of displacement in a time of 20 seconds. So how powerful is the work during that time? Plug all your good values in there. I believe the mu is given 0.2 right up here. So plug in 0.2 times the normal force. Ooh, don't let this trick you a little bit. Normal force is not just the weight. Remember, there's a downward component to this force. So we're going to add that downward component to the force. I guess that would be 100. Let's see, 10 times 9.8 plus F sine 30. Okay, so the force is 100, sine 30 is 1/2. So that's the total normal force. So that's where that character is coming in. Got mu times the total normal force. Okay, don't forget those characters in there, especially when you got that force pushing downward or force lifting upward. Don't jump to that conclusion that normal force is equal to weight. That's something that'll trick you. And finally, take that force, mu times normal force is the friction, multiplied by the displacement, divided by 20, and we get negative 75 watts. So this system, we got 217 watts of power of the push, and negative 75 watts of power. The friction's working against the push, so you can get the power, the unpower there. All right, moving on, conservation of energy. Sometimes you'll just get this random question and you'll be like, oh, what do I do with this? So what are some indicators that you should turn to conservation energy to solve it? If there are any changing heights, like a pendulum or a roller coaster, conservation energy, start thinking about it. Can I apply conservation energy here? If there are changing velocities, is there a change in kinetic energy? Then there's work done, and that work will give you a change in kinetic energy and a negative change in potential energy. If there's any springs involved that are compressing, you'll probably want to turn to conservation of energy. All right, so in this scenario, there's a little bit of everything. We've got a change in a height from this cart rolling down the ramp. That's going to cause a change in velocity as it gets faster and faster. And then there's going to be a compressing spring at the end. So a big question here might be, what is the maximum compression of the spring? What is the velocity at the bottom of the ramp? So in all, the way to conceptualize conservation of energy is that energy at one point equals energy at the other. And where is this concept coming from? Just if you roll it back a little bit, actually all the way to the beginning, that work done as that roller coaster falls down is going to give a positive change in kinetic energy, but it'll also produce a negative change in potential. So conservation of energy really comes from work. It's coming from this expression right here. If you plot the potentials at one point and the kinetic energies also at, the potentials at those 2 points, point 1 and point 2, and also the kinetic energies at point 1 and point 2, rearrange them algebraically, put all the initial conditions on one side and all the final conditions on the other, then what you come up with is energy 1 equals energy 2. That's what I'm starting with here. Okay, so back to it. We can think of the cart at the very top. Let's call that point 1. Or actually, let's call this the initial position 0. We're going to call the bottom of the ramp point 1 and maximum compression point 2. So energy at 0 equals energy at 1. That's what we're going to start with here. The energy at the initial starting point, it's moving with the starting velocity. It has a initial height of 4, so it has kinetic and potential energy. At the very bottom of the ramp, there's no more height. So the height is 0, mgh will be 0 as well. So there's no potential energy, but it's going to be moving faster. So let's plug in kinetic energy plus the potential energy. That's the total energy at the start, and kinetic energy at point 1. Substitute in kinetic energy expression, substitute in the potential energy expression, and kinetic energy at point 1. We plug in known values, 5 at the beginning, 4 meters high, and what is the unknown velocity? 10.2 meters per second. Now, next, what are we going to do for compressing the spring? Well, if energy at point 0 equals energy at point 1, and energy at point 1 equals energy at point 2, then it goes to show that energy at point 0 is also equal to energy at point 2. If A equals B and B equals C, then A equals C. So we could use any one of those. You could start with the same expression on the left, 1/2 mv squared plus mgh initial. But I think this, since we do have the velocity at point 1, that's just a little easier to plug in there. Now keep in mind, there's a neat thing that happened here. Just jump back a little bit. The masses canceled right there, and right here. There's a mass term in each one of those, and they all canceled. So be careful that you don't just go willy-nilly and plug in 1/2 times 10.2 squared down here, because when you compare kinetic energy to the potential energy of a spring, which we're going to look at right here, the masses do not cancel. This is a K, not an M. You do get 1/2 canceling, but you will need to plug in that mass again. So 1/2 mass times velocity squared equals 1/2 K. The given value for the K in this problem is 1,000 newtons per meter, and then delta x squared. So as long as this spring is uncompressed, if it's at its rest position to start with, it's usually what would happen in a bumper kind of spring like that, then the delta x would be the change from the initial of 0 to the final of 3.2 meters. That's how you'd solve that one. Okay, so that gives you a little bit of everything there. Foundations of work and kinetic energy and potential energy, forms of potential energy, introducing kinetic energy and power, and finally a little application of conservation of energy. And we'll see that again when we revisit it in the rotation section of the review. Thanks for watching. Hope this is helpful.